Hey guys, this is Professor Janacek. I want to talk about planes and surfaces. So back in our 2 space, we can find a line if we're given a point, I'll call it x1, y1, and the slope, we'll call that m. You've probably done this before. We've got the formula y minus y1 is equal to m times x minus x1. Of course, we could turn that around, move some stuff here and there, and write it as m times x minus x1 minus 1 times y minus y1 is equal to 0. So notice I just moved the y minus y1, put that in a group, move that collectively over to the right-hand side of the equation, set it equal to 0. Of course, I turned the whole thing around, so the right side is now the left side, vice versa. Of course, we can also write that instead of m's and stuff. Let me just replace this, write it as a times x minus x1 plus b times y minus y1 is equal to 0. And of course, you can see that there is a connection between m, negative, and negative 1 with a and b. Of course, you can also, if you remember the another form of an equation, just ax plus by is equal to some constant c. Again, a typical way of writing an equation of lines. There are other ways, but these are just some basics, basic forms of lines. So that's in R2 space, and that's a line. Now we have a similar idea in 3 space, and that is a plane. So in R3 space, if I want a plane that goes through the point x naught, y naught, z naught, and it'll have a non-zero normal vector which we label as the vector a, b, c. I'll talk more about what a normal vector is in just a second. You'll see when we kind of work through this. So it's got something, instead of a slope, it's got a non-zero normal vector. So just like this, the point is kind of a starting spot in R2, same thing goes for R3. The point is my starting spot. My slope kind of gives me direction from there, and my normal vector also kind of gives me some direction in this. So using the same idea, I've got this normal vector, I've got this point. The equation of the plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. And of course, you can see where all these values come from. X naught, y naught, z naught, a, b, and c are all values that were given, and then we just put that into the equation, and there you go. It could also be written, this is very common, oops, there it is. We could also write this as simply ax plus by plus c is equal to 0. I'm sorry, is equal to d, and that would be for d equal to ax naught plus b y naught plus c z naught. Okay, and there you go. That's the equation of a plane. Now, looking at that normal vector, notice again it kind of gives us their direction. I want to make note that all vectors in this plane, so if I've got a plane, a surface here, there's a plane, all the vectors in this plane, no matter what direction they're going, all the vectors in the plane are orthogonal to the normal vector. And that's one way of defining a normal vector. It is the vector that is orthogonal to all vectors in the plane. So the normal vector would go this direction. Okay, a couple of things to, of course, the normal vector could also go the other direction, just so you know. Now, some things about these. Two planes are parallel if their normal vectors are parallel, meaning, so I've got a plane here and a plane there. Those two we'll say are parallel if I look at their normal vectors, and those are parallel. Notice the normal vector and the vectors in the plane, of course, are orthogonal, but they would both have to be parallel in order for the planes to be parallel. Two planes are orthogonal if their normal vectors are orthogonal. Again, remember the normal vector is not in the plane, but it does help us with the plane. So here I've got one plane here and another plane there. They're perpendicular or orthogonal to one another, and turns out that their normal vectors are also orthogonal. Again, just remember the normal vector is not in the plane. It is orthogonal to the plane, but it can tell me a lot about what's going on in the plane itself. All right, so that's looking, we were looking here at lines and in R2, and they relate to planes in R3. So lines in R2, a lot like planes in R3. So curves in R2 will actually relate to surfaces in R3. So curves, there's all kinds of equations of curves. I won't have time here to go through all of them, but you probably remember like quadratic curves. Right, the curve whose graph is a parabola, say. Well, a quadratic curve in R2 space can be represented, we can extrapolate from that and get quadric surfaces in R3 space. And just so you know, cylinders are actually types of quadric surfaces. One thing we like to look at with a surface of any sort, whether it's quadric or not, and here we do have some quadric surfaces. What we'd like to look at is their traces. A trace is a set of points at which a surface intersects a plane. Very specifically, we can look at when it intersects the xy plane or the yz plane or the xz plane. But think of this, you could think of this as a cross section, or maybe just a slice or a shadow. These are all concepts that kind of connotate what we're looking at with a trace. So you can see here we have the xy trace. So this is along the xy plane. That's the trace we have. Or the yz trace. Again, that's along the yz plane. So if you look at the plane that the y-axis and z-axis make, and what does that look like? What is the intersection if I were to slice it along that plane? Or the xz trace. You can see that one as well. So again, if I were to take a plane and slice any one of these, what does that look like? Well, that's what we call a trace. So to find a trace, if I want to find the xy trace, then what we'll do is we'll let z equal to 0. To find the yz trace, we let x equal to 0, and to find the xz trace, we will let y equal to 0. Right, pretty straightforward. Enjoy!